Hi, everybody. My name is Dr. Brad Holschuh. I co-direct the University of Minnesota Wearable Technology Lab with Lucy Dunn, who we heard from earlier today. I'm a brand new faculty member at the University of Minnesota. I started in January. We're in the College of Design in an apparel studies program, but my background is in aerospace engineering. I spent the last 12 years of my life at MIT in the aerospace department working on spacesuit technology. So at MIT, that makes me an aerospace engineer. At Minnesota, it makes me an apparel designer. But what I'm going to talk to you about today is something that I think is a little bit different than what we've heard about, at least the talks that I've been able to listen to, and this is actuation in wearable systems. So thinking about what this means, wearable technology, as we all can appreciate, is rapidly moving forward. The things that we see coming to market tend to focus on the sensing and computing sides of things. So interpreting the world, interpreting the person, making sense of the data, and then providing the data, either in real time or sometimes retroactively. The thing that seems to be missing for the largest part of this problem is actually providing physical input to the person. Physically affecting the person, closing the loop, literally and figuratively, to affect the wearer. And that's something that I find really interesting. And it can be done in a variety of ways. Obviously, exoskeletons are something that everybody can appreciate. But what I like to think about is not your typical electromechanical solution. So not adding servos to the body, cabling to manipulate the person, thinking about this from the material level. And in particular, there's a category of materials that fall under the moniker of active materials, artificial muscles, smart materials. They've got a bunch of names, but these are a broad category of materials that have the ability to change themselves under stimulation. And what I'm most interested in are these materials that can change dimension. And so if you start thinking about working with these materials, putting them on the body, suddenly you have the ability, potentially, to produce forces, displacements, tensions, pressures, whatever it is that you're interested in, on the body by virtue of the material itself, without any type of exotic manipulator or servomechanical system. There's a wide variety of these materials, and they come in many different form factors, capabilities, characteristics. And that's because artificial muscles are a broad term that can apply to anything that can be stimulated to change itself. So these can take the form of shape memory alloys, shape memory polymers, carbon nanotubes, electroactive polymers. This is an entire industry in and of itself. And every one of these materials operates a little bit differently. So if we want to think about putting this on the body, the first thing that we have to think about is what type of force and displacement do we want? What type of form factor does the material take or can it be manipulated into? And what type of stimulation or power is required to produce the effect? You know, some of these materials might have really incredible properties, but if they require a superconducting magnet or kilovolt level voltages, it's a non-starter if you think about putting it on the body. I'm going to give you a quick case study in one of the materials that I've studied in the past and I'm continuing to study, and these are shape memory alloys, and in particular, shape memory alloy springs. Shape memory alloys are a material that many of you may be familiar with. They're probably the most commercially mature of the active material landscape, and these are metals that can change shape when you heat them up. And I won't get into the physics of why this happens, but at the end of the day, when you talk about it from a design or an engineering perspective, these are materials that you can imbue with a memory state, and when you heat them up, they will physically transform into the shape that you prescribe. They typically can be bought in wire form, and they'll either straighten out or shrink by a few percentage points. But to me, what's most interesting is to form these into springs and to imbue them with the memory characteristic of the shortest form of that spring. And what that means at the end of the day is you can take these materials and deform them, what have you, at cold temperatures, heat them up, and produce a recoiling effect. And you can produce significant forces, and when I say significant, I mean in the single to double-digit pound ranges. You can produce displacements of 50 to 75% of the length that you started with, and you can do it through a simple applied current. And I have an example of what these look like in practice. I think it's running. This is one of our actuator cartridges that uses these springs. So, for example, each one of these springs is about 1 millimeter in diameter, and this is producing 20 pounds of pulling force. And you can package it into a small cartridge like this to produce localized, again, force, tension, pressure, displacement, what have you, to actually physically affect the person. So going beyond sensing what's going on, sensing their orientation, sensing the environment, taking that data and actually doing something to the person for net benefit, whether it's performance increase, health benefit, what have you. A criticism of these materials is that they can be power hungry. They might require continuous activation to produce an effect, and that's true for the springs that I just showed you, but that doesn't mean that we can't solve the problem. So that cartridge that I showed you in the previous video, in order to sustain the pulling force that you saw, it needs to be continually powered, or at least continually heated. That doesn't mean that you can't combine it with some very simple mechanical structures to produce a sustained effect on the person. And so here, this is an example of the same technology built into your run-of-the-mill buckle, and suddenly you can make garments that will squeeze closed and latch themselves closed. So you only need a very temporary infusion of power to produce a compression effect that will be maintained in perpetuity until you let go of the mechanical fixture. So this is a compression garment that can produce 10 times the amount of pressure of your medical grade compression stocking. And you might say, why would you ever want to make a compression garment that tight? This is motivated in the aerospace world. We actually saw a picture of this in an earlier presentation. There's a proposition to completely redesign the spacesuit that's used by NASA, and that's to make it skin tight. And I'm not going to go into the details of it, but in order to make a skin-tight spacesuit work, you need to replicate 1/3 of an atmosphere on the body to protect you against vacuum. And that 1/3 of an atmosphere translates to about 10 times tighter than a medical-grade compression stocking. At MIT, we studied the development of the suit, and about the only way possible to implement this type of architecture is to have the materials be active. And so we demonstrated through these shaped memory alloys that you can literally squeeze somebody 10 times tighter than any garment that's ever been worn for commercial purposes, and all it takes is a very temporary applied current to produce the effect. So I'm going to spend the last few minutes of my talk showing you a few different applications that we're thinking about here in our lab, but certainly this isn't the limit to the way that wearable actuated systems could be implemented. So as I mentioned, dynamic compression garments. We're beginning a collaboration with the Mayo Clinic in Minnesota to produce clinical grade compression garments that can be strategically activated. So if any of you have ever worn or know somebody who have worn a clinical compression garment, they typically take the form of either a tight fitting stocking or an inflatable garment. And we can do better than both of those things. We can make a garment that's incredibly easy to put on. You flip a switch and it tightens. And it tightens strategically. It can be synchronized to other parts of the garment. It can be synchronized to your biosignals to produce literally a dynamic compression environment that has a whole host of possibilities. We've begun developing compression garments for autistic children. So there is very strong evidence that compression therapy is useful to calm somebody who's overstimulated, especially if they have sensory processing disorder. The catch-22 to this problem is that typically children who are overstimulated don't want to be approached by someone to be calmed down. So we've made a compression garment that's Bluetooth activated that can be squeezed by hitting a button on your iPhone. And you can use this to apply pressure remotely to somebody who needs compression therapy. This was presented at a conference in February, the Augmented Human Conference in Switzerland, and took first place by a student in our lab. And we're going to undertake in the next year human subject testing on actual autistic populations to demonstrate the efficacy of this approach. We think often about battlefield medicine. So what I've shown you, another way to think about controllable compression is controllable tourniquet. And this is a very easy type of system to implement into the uniforms that we put our soldiers in when we send them out to the field. How incredible would it be if the clothing that our soldiers are wearing could tourniquet on command? That could save lives if you incur an injury in the battlefield and you don't even need a medic around you. Your clothing can tighten and tourniquet you and save your life. Orthotics, casts. Anybody who has ever had their leg in a cast or an arm in a cast, or who maybe had scoliosis. These garments constantly are custom made, have to be updated over time to produce an orthotic regiment that can correct the underlying issue. What if your cast or your garment is dynamic and can apply forces that change placement and magnitude over time? You can do that with these types of materials. And finally, like I said, this is just the beginning. You see here on the left, this was the very first foray that Lucy and I did when I joined the University of Minnesota, and it was to make the shape-changing jacket from Back to the Future. You can take this to whatever level you want, but damn it, it's 2015. Back to the Future said we should have shape-changing clothes. We can do it if people are willing to invest the technology, and we demonstrated it last fall. So I'm happy to talk ad nauseum with the way that these materials can be used, but I think I'm out of time, so we'll leave it there. Thank you.